Okay, kind of the next objective that we want to cover, we've talked about the unit circle. We've done a couple problems that relate to a unit circle and one review problem. And then what we look at now is the domain and ranges of the 6 trig functions. And knowing this information will be really helpful when we get to especially inverse trig functions. If we're not solid on these, on the domain range of each of the 6 trig functions, then we're going to be really shaky and not really confident when it comes to the inverse trig functions. So what we want to do is take a look at this picture from the textbook here, and it shows a unit circle, and they have a point on the unit circle, and it's labeled AB. I'll highlight it. Here's the point AB, and we'll make it red. So here is this. That coordinate is AB. And from before, in a previous section, we learned that if we just know the point on a terminal side of the angle, and then this length right here, the distance from the origin out to the point, if we know that length, then we can come up with all 6 trig functions of that particular angle theta. And so that's all this is over here. It's showing that the sine of theta is b. Well, why is that? Well, if we use if I use the reference triangle here, I can use that if I want. Reference triangle, we'll use the angle alpha here to help come up with this. So opposite over hypotenuse would be b over 1. And since our radius is 1 on the unit circle, then that would just be b. b over 1 is b. So the sine of theta is just the b coordinate of this. Well, and that makes sense to us because we know if this is the unit circle, then the y coordinate, or b in this case, is the sine. And the same thing goes with the cosine, is that this x coordinate, or a, is the cosine. Let's take a look at the graph of the sine function. This is not the graph of the sine function. This is a unit circle that actually tells us what the sine and cosine values are as we move the angle around. But let's take a look. I've gone to the website Desmos here, and I've got the graph of the sine function. And you can see along the x-axis we have the angles in radians, starting here at 0, and then here's pi over here, and if I zoom out a little bit, you'll see here's 2 pi. And then on the x-axis, on the y-axis would be the sine values, since I'm graphing the sine. So again, on the x-axis, remember x-axis is the domain, represents all the possible values in the domain. And for a trig function, what's in the domain? Well, what's in the domain are angles, because I'm taking an angle and plugging it into either the sine or the cosine or the tangent or whatever. And so the inputs, or the domain, for any trig function is going to be an angle. So I have along the x-axis the angles, and then the y-axis would be the outputs from the function, which would be the sine values. And here you can see, let me zoom out. This graph goes on and on to the right and to the left of the origin here. Let me go ahead and I'll put the arrows on the axes so you can see where the x and y axis are. Well, I keep zooming out, then that graph keeps going off far to the right and keeps going and off far to the left. So that tells me my angles, I can put any angles I want into the sine function and I can get a valid sine value. So that tells me that the domain of the sine function is all real numbers. I can plug any angle I want into the sine function. Now what about the range? Well, the range is basically from the graph. You can say, well, how low does it go? How far down on the y-axis? And then how far up does it go on the y-axis? Well, you can see here it bottoms out at -1. That's the lowest y value, or sine value. and then it goes as high as 1 on the y-axis here, and so that would be the highest sine value. So the range goes from -1 to 1 and all values in between. The graph is not broken up at all. So how are we going to represent that here? Well, what we do is we'd say, okay, I'm going to use D for domain, and we'll use R for range. So we said anything goes as far as angles. We can plot any angles we want. So -infinity to infinity would be our domain, and the range was anything between -1 and 1. Remember, the square brackets means it includes the values of -1 and 1 also. Now we're going to do a lot with the graphs here in the coming weeks, but I just want to use the graph to help us look at the domain and range. Let's also put in here, I'm going to put the cosine function, and I'm putting both graphs on the same grid here, and you can see they're very similar. It's just that the cosine is shifted a little bit from the sine. So let me turn the sine off. And what you might notice is that, look, when I zoom out, the graph keeps going on and on and on to the right of 0 on the x-axis and to the left of 0 on the x-axis, and it keeps going, which again indicates that, hey, the cosine also has a domain of all real numbers. I can plug any angles I want into the cosine. Also look at the range. It goes as low as -1 and as high as 1. And so what we have is that the sine and cosine both have the same domain and range. -infinity to infinity, which is all real numbers in interval notation, and the range -1 to 1. Now the tangent's a little bit different. Let me go back to look at this in the yellow block up here. It says the tangent of theta is b over a, but a cannot be equal to 0. Now why would that be? Well, it's because you can't divide by 0, and since a and b is just a point on the unit circle over here that we can move around at different angles, it is possible that that point could stop where a would be 0, the x-coordinate, which would be straight up and down at 90 degrees, or straight down at 270. So what I have to do is I have to basically find out how to describe all those angles where this tangent function would be undefined, where a would be 0. And it's going to be anytime the angle is 90 degrees or a multiple, actually an odd multiple of 90 degrees is the way we'd want to say it, because straight up or straight down. So either any odd multiple of 90 degrees or pi over 2 would do it, because if I think about this as pi over 2 here, it's not going to be 2 pi over 2 because that would be over here at pi. But 3 pi over 2 would work. So 1 pi over 2, 3 pi over 2, and then if I go back up here, it'd be 5 pi over 2, and back down here it'd be 7 pi over 2. So every odd integer multiple of pi over 2 is going to be an angle where the tangent is undefined. And let me just show you how that looks on the graph of the function of the tangent. So we pull up the tangent function here. Let's put that in. It looks quite different from the others. So let me turn off the cosine graph. So here's our tangent graph. You can see it looks like a backwards S curve almost. But you'll notice vertically there are some spaces in here where there's nothing, there's these jumps kind of between the graphs. And I'll put some vertical lines in here just to show you that they are at these odd multiples of pi over 2. So let's say x equals pi over 2. So that purple line I threw in there is right at pi over 2. And you can see it goes right between these two green parts of the tangent curve here, the green graphs, which is the tangent curve function. But it doesn't touch those the green lines. So, and that's asymptotic behavior. We've seen that in other functions before, where you have, as you approach a particular number, if the graph goes straight up or straight down but never touches this, never crosses this value for the domain, then that's the indication of that there is a vertical asymptote. And that's exactly what that is. Let's show you there's another one. We said odd integer multiples. So let's try 3 pi over 2. And that's where this black line is. So you could see that is indeed a space where there is some vertical asymptote there. And I keep going odd multiples of pi over 2 to the right of 0, or I could also go to the left of 0 odd multiples of pi over 2. But I'm just trying to show you that there are values, there are angles for which the tangent function is undefined. So when we write down the domain of the tangent, that's what we have to consider. If there are exceptions to the domain, if there are values that we cannot plug in for angles. So our domain for the tangent is going to be all real numbers except odd integer multiples of pi over 2 or 90 degrees. That's our domain for our tangent. Now what about the range? Let's get the graph back up here. Well, these, the range again, how high up does the graph go for y values, for the function values? Or how low does it go? Well, you could actually put arrows on each one of these green lines going up and then one going down at the bottom. So they go up forever, they're going down forever. So that really indicates to us that our range is all real numbers. So our range for our tangent is all, well, we're going to say that with interval notation. So negative infinity to infinity would be that. Okay. Now let's talk about the cosecant. Look up here in the yellow box. Cosecant of theta is 1 over b when we're talking about the coordinates, which makes sense because the sine was b, then the reciprocal is going to be the cosine. But remember, since we have something that can change down here in this denominator, that b, if it's 0, will be dividing by 0. So we have to exclude any angle that would have a b coordinate, which is the y coordinate of 0. Well, where are the y coordinates 0 on the unit circle? Well, over here straight to the left, negative 1, 0, which would be at 180 degrees or pi. And then over here at 0, we also have a y value of 0 or b of 0. So I need to find a way to describe any angle that would put me over there at 0 or at pi. Probably the easiest way to describe that would be all integer multiples of pi, because you could have 0 pi, 1 pi, 1 pi, which would be over at 180, right? And then 2 pi, which would put me back kind of over where 0 was, and then 3 pi puts me back over at 180. So just integer multiples of pi or 180 would be the domain for that. So let's go ahead and say here we've got cosecant, so cos secant, and the domain is all real numbers except integer multiples of pi or 180. Okay. Now, let's take a look at the graph of the cosecant so you can see that real quick. CSC for cosecant. Now this looks quite different too. Remember how the sine function, if I turn the sine on, which is the reciprocal, look what happens. It fills in that middle space that's not included in the cosecant. So let me turn the sine back off. But whereas the sine fluctuated between, the sine values fluctuated between 1 and -1. The cosecant is just kind of, in a sense, the reverse of that, in that you can see here it's everything above, the range would be everything above 1 and then everything below -1. So that's the range. But then you can certainly see here that integer multiples of pi is where there are some vertical asymptotes. In here I put a blue line showing the space here where there's this space between these parts of the red graph, and the red graph is the cosecant graph. And actually, the way I would describe this, just kind of in layman's terms, not in mathematical terms, but these are like little mini parabolas, these little curves here. And these open up, and down here below would be like little mini parabolas that open downward. And they would have arrows on them, too. But we have these vertical asymptotes in here that are all multiples of pi. So let's put another one in here, like -2 pi. Here. So I jumped over here and put one in here. You can see any multiple of pi is going to be a place where there's a vertical asymptote because the cosecant is undefined at those angles. So, but the range, what we need to do for the range, again, is describe all of the y values above 1 and below -1. So let's go back in here, and for the range, we're going to say is -infinity coming up to -1, bracket, union, jumping up to 1 with a bracket, and then to positive infinity. So that would be the range of the cosecant. Let's take a look at the secant. It's going to be very similar here. It looks similar, all right? So let's just go ahead and put up in here the secant. Very similar, it's just shifted. So now notice here we have a no man's land in here, sort of a vertical asymptote in here. It's halfway between 0 and pi. It looks like pi over 2. So pi over 2, and then 3 pi over 2, and then 5 pi over 2. Looks like odd integer multiples of pi over 2 seem to be a place where there's vertical asymptotes. And we had that before with something else. Up here for the tangent we had the exception from the domain of odd integer multiples of pi over 2. So the secant's the same. It has the same domain as the tangent. We're going to say all real numbers except odd integer multiples of pi over 2 or 90 degrees. And you can see the range is the same as was the cosecant. Right? It's like these little mini parabolas facing up and then facing down, but from 1, the y value of 1 upwards to infinity, and then also from -1 downwards to -infinity. So it's exactly the same range as the cosecant. So we have range -infinity to -1, union 1 to infinity. Then one more trig function to go, then we'll take a break here. So we've got the cotangent. Okay. And so with this, we'll do the graph again. Okay, so turn off the secant. So now the cotangent looks similar to the tangent, except for the curve is going the opposite direction. If I turn the tangent back on, you'll see the curves go the opposite direction. So here's the cotangent, and you'll notice, again, there are vertical asymptotes. There are locations where the cotangent function is undefined. There are angles for which the cotangent is undefined. You can see here, it looks like it's 0. So if I type x equals 0, there's a space. And then it looks like over here at pi, let's try that. So x equals pi, and then 2 pi, and then 3 pi, and then you could go backwards, negative pi, negative 2 pi. So it looks like all integer multiples of pi would be a place where this function is undefined. So we'll go ahead and put that in for the domain. So we got our domain is all real numbers except integer multiples of pi, or 180. And then the range, same as the tangent, as you can see, because these graphs, these get rid of those vertical lines there. These the upper part of the cotangent function goes up forever, as well as the lower parts here, they go down forever. So negative infinity to infinity would be the range there. Okay, so those are that's the domain and range of every one of the 6 trig functions, and we're going to need to remember those. It's important for you to memorize those. We'll revisit them as we do the graphs of the functions, because basically after we get through this section, it's about graphing the 6 trig functions. And we were even able to identify the domains and ranges of these using their graphs. So as well as kind of looking at the diagram up above here. So those are the domains and ranges. We got to remember those.